All right, so our next talk is by John Bonini from Rutgers University on Berry Flux diagonalization application to electric polarization.
I don't see it. Okay, so I guess regardless of any other controversy, one thing I think we do agree on is that the modern theory lets us compute a change in polarization along a known path, along a known switching path. So the thing, as Ron pointed out, I almost want to steal that slide of all the domain walls moving and things, is that we often, from first principles, don't really know the actual path. So in my talk, I'm going to tell you why we can compute spontaneous polarization anyway, and how we can use that insight to compute it more efficiently. All right, so ferroelectrics, as was mentioned here, if the spontaneous polarization is measured by integrating the current that occurs during the switching process. So we have the hysteresis loop here. The vertical axis is marked as P, but it's really integrated current. As the material switches, I have a little cartoon of like up and down in our perovskite. So how do we predict this now from first principles? So in general, as I mentioned, it depends on really the dynamics of the switching process, what happens in between these two up and down states. But with certain assumptions, we only need, I'm going to claim that we only need the initial and final states for most ferroelectrics. So first I'm going to do a little bit of background. That slide that Ron kind of glazed over, I'm going to just set up the notation that we're going to need here. So the modern theory tells us that for a given adiabatic path, we can express the change in polarization as this Berry flux. Here I'm only looking at the electronic part, and for the moment only in one dimension. So we have this Berry flux given by this capital phi, which is the integral of the Berry curvature on this 2D surface here. The Berry curvature is given down at the bottom in terms of the block wave functions here. And it's this quantity integrated over this k lambda space. Here, k, we're in 1D, so we only have one reciprocal lattice direction, that's k, and lambda is parameterizing this switching process. So we want to compute this from first principles, and usually we don't actually have these block states on this entire surface as continuous entities, so we need to make a few changes. What's typically done is we can use a Stokes theorem to, instead of finding the integral of the curvature over that whole k lambda space, we can define a vector potential, the Berry potential around the boundary, and integrate that just at the edge. So I've defined this Berry potential here, but just like in classical electrodynamics, when you go to a vector potential here, you have a gauge freedom, which comes up as a unitary rotation that can act on all of the bands at any point k lambda here. That we'll come back to that soon. The next thing one usually does is say, well, these two horizontal parts, the ones that you're integrating along the lambda directions, are separated by a reciprocal lattice vector, so their contributions actually cancel. And then you define these phases that you get one at each state, which you can think of A as like maybe a polarization up and B as polarization down. And so we can get this Berry flux as the difference here. These phis are related to the formal polarization that we just heard some things about. Now these phis are gauge invariant up to some integer multiple of 2 pi, and this is where the whole polarization, where the controversy in the last talk came in. One last step to get to realistic calculations is usually we only have the wave functions at discrete points in k space, so there's a version of this is sort of like the discrete analog of the Berry potential here, where now we have overlaps of wave functions going from one set of 1k to the next, and we take the imaginary log of the determinant of this overlap matrix. And then of course we can just keep adding up the phase accumulated as we go around to get the phase at each state. So now, as I mentioned, and as was discussed just a moment ago, that how do we take this difference when we really only have these phases only known modulo 2 pi? So I compute one of them, I get the polarization lattice again, and we say, well, how do I take a difference of two lattice quantities? There's the gauge freedom and such, and the fact that they're really just multi-valued quantities. It seems like we need more information or some sort of an assumption to properly take this difference. So my claim is going to be that we're going to do this without computing any more wave functions. And so our physically motivated assumption is going to be that we have some small change in our Hamiltonian, and that's going to lead to some minimal evolution of a number of individual wave function phases in the wave function. So the more information we're using is going to be more phases we're pulling out of the wave function rather than this total change in formal polarization. So we're going to separate this Berry curvature into as many gauge invariant parts as possible. There's going to be something like a contribution from each K point at each band, or at least a contribution for each band. And it'll be these contributions which we're going to assume remain small. So let me make that a little more precise. We can separate the surface into a number of plaquettes. I'm going to label each one P. So the total Berry flux that we were interested in computing will be the sum of the fluxes from all of these little plaquettes. And we can get the flux through the plaquette using the same sort of Stokes theorem argument where we go with this sort of discrete Berry potential around the edge. But I'm writing it in this way where these are multiplied out because then this ends up being a gauge invariant quantity. So this now would require overlaps of wave functions from going from structure A to structure B. You really need to take this is something that's not implemented in most codes, and that's how we're accounting for, that sort of accounts for the difference in gauge that might be occurring there. So that's one way we could start separating this flux into a number of smaller contributions, but we're going to go a step further and separate each of these plaquette fluxes into a number of phases equal to the number of bands that are there. So we're going to perform a singular value decomposition, which factors each of these overlap matrices that correspond to the green arrows here into two unitary matrices and a real diagonal matrix of singular value whose elements are called singular values. I'll come back to them soon. So we can make a unitary approximation of our actual overlap matrix, which pretty much captures all of the phase information that was in these overlap matrices. And the product of these unitary approximations going around the loop forms its own unitary matrix. And so if we just wanted the plaquette flux, we could get that from the imaginary log of the determinant of this U, which is the same as what we computed on the last slide. But the advantage of doing this is that it's going to have eigenvalues that are of this form e to the I phi. And it's these phi's we'll have one for each band. We'll have the same number of phases as the number of bands anyway. And these are what's known in other contexts as Wilson loop eigenvalues. In this context, I'm calling them diagonalized Berry fluxes because they are, if this overlap matrix, if we were in a gauge that diagonalized this overlap matrix, which you could construct actually from the eigenvectors, but we're going to then, if you did construct that gauge, then it would be like this rotation around the plaquette. It has diagonal elements for the phase. So you'd kind of diagonalize the Berry flux. And it's going to be these smaller phases that we assume are smaller in magnitude than pi, and that's sort of the key assumption here. So everything so far was in 1D. The generalization to 3D is actually quite simple. The only thing that changes in our formula is, one, we have a factor now of this lattice vector over the cell volume that shows up. And then just as is done in formal polarization calculations, you create a number of strings in K-space that are along the reciprocal lattice vector that's dual to the polarization direction of interest, and then just average over them. So we would create one string in one material and actually use the corresponding string in the other state, maybe one's in up, one's in down, and find the flux that corresponds to that string, and then just do that with all of them and average them. So okay, I can show you some actual real results. So if we take ferroelectric lead titanate, so I'm just showing plaquettes from a single string, and what I'm showing here are the distribution of these individual phases, these diagonalized Berry fluxes or Wilson loop eigenvalues. I've marked the plaquette it corresponds to. If I do like a 6 by 6, or I guess it's 6 along this direction sampling. Some of them have 2 plaquettes highlighted because those plaquettes are related by time reversal symmetry and give the exact same set of Wilson loop eigenvalues. So we have a number of, these are our smaller phases that we assume are small. We actually see that they don't get much larger than pi over 6, so they're staying small with respect to pi. If you go ahead and sum all of these up, that gives us this Berry flux corresponding to this string. We average over the string, and we'll include the ionic part. And just from the up and down state, we're getting the change in polarization. I'm dividing by 2 because that's how spontaneous polarization is defined for lead titanate. So I want to look at, I'll go back to this formula here. We have this lattice vector over the cell volume, and in other approaches, this can lead, when this factor becomes small, things can get tricky because a 2 pi ambiguity here leads to very closely spaced allowed values in delta p. And this often comes up, I think Ron hinted at, in supercell calculations where somehow you go to a supercell and it seems like your problem becomes more difficult. And I'm going to show that's not an issue in this approach. So on this slide, I've taken my, what I showed you before and sort of turned it on its side and put it on the right is the primitive cell Wilson loop eigenvalue. Oh, no. All right, our primitive cell Wilson loop eigenvalues are on the right, and what's on the left is the corresponding string for a supercell, and it looks like they are exactly the same, except if you pay attention to the scales down here in the supercell system, everything is multiplied by a factor of 4. So we see all the same eigenvalues occur, there's just 4 times as many of them. You can look at how this comes in, is we have 4 times the Berry flux. So if all we were tracking was this total phase, this would become much larger than 2 pi, and it would seem like we have issues. That factor of 4 is canceled out in the volume, so of course we get the same number. But since we're just seeing all the same individual phases, there's no difficulty in some phase becoming too large. It's, we have 4 times the change in dipole moment, which makes it much larger than the quantum of polarization, but all the individual contributions are the same. There's just 4 times as many of them. You might worry that these are all coming out so precisely the same because of some symmetry in here. All the symmetries were turned off when the calculation was done, but just let's replace one of the titaniums with zirconium, and also to make it a somewhat more realistic calculation, because who's going to compute the polarization in a big supercell anyway. And of course the values do change, and we see some changes here, but we get the same, they're mostly spanning the same range of phases here, not getting much larger than pi over 6 in magnitude, and we can directly in this supercell system just use the first and last, the up and down states, and compute the spontaneous polarization. So I said I'd come back to the singular values. We're going to use them as a sort of built-in check that our systems are closely related enough that the method can be applied. So while we use the unitary parts to pull out these individual phases, the singular values correspond to sort of like the norm of this complex number we're pulling the phase from. And if a norm of a complex number gets too small, it's sort of useless to talk about the phase. So I'm just taking the overlaps from structure A to structure B, like up to down at the moment. So I take each of those, kind of what this picture is showing as I'm going from one structure to the other. And I take, for each k point, I take the overlap with the corresponding k point in the other structure, do this singular value decomposition. And what I'm plotting here is not a band structure, even though it's the way band structure, it's for each, even though this is the way band structures are often plotted, it's for each k point we have, a set of singular values, and we're seeing that none of them fall below 0. So this is sort of a built-in check you get with the method. When you apply the method, you should make sure that none of your singular values become too small, or the structure changed too much for the approximations and things we're using to hold. So just quick comparison to previous approaches. If you did the thing where you have to compute along some path, the path you're using is somewhat fictitious, as we saw before anyway. To just do the primitive cell of PTO, I needed 3 intermediate points, and then when you go to the supercell, suddenly you need like 16 intermediate points to resolve this, how the polarization difference changed. But with this method, in both cases, I'm only using the 2 endpoints. And that's because we're really pulling more information out of the 2 wave functions. We're getting all these individual phases instead of just getting their sum directly. Furthermore, we're accessing the change directly. We're not computing polarization, formal polarization at each point and taking a difference. We're sort of just pulling out the spontaneous polarization, the number of interest, the thing that's actually measured. There's a built-in check to know if we're in the regime where this sort of thing is going to hold with the singular values. Supercell systems don't complicate our calculation any more than the fact that there's just more atoms in it. There's no branch issue that they will typically cause. And since this isn't the real switching path anyway, just because you get a metallic point at some intermediate state doesn't necessarily mean a real material is going to go through a metallic state. So this gives you a chance to, where this method you would get a metallic point and wouldn't know what to do, you can kind of sidestep that by going to, like, making this approximation going directly from up to down. So quick summary, by assuming this minimal evolution of all of these individual phases, we're able to compute the switching polarization without any intermediate calculations along a path. I've implemented this as sort of just a one-shot. You have your wave functions at the moment just for Abinit, but other codes will be implemented soon. It's post-processing step for Abinit. There's a check out my GitHub soon. I'll have a link to the paper there when it shows up on archive. JRBP, which is just my initials with a P for physics. So thank you.
All right, thanks. Do we have some time for questions?
Nice. I wonder, is this method miraculously working for all materials, or is it just a tool which most likely will work?
So like I said, you really need your systems to be closely related enough that you can get overlaps of wave functions between your two different states. If those overlaps become too small, then you can't really say anything. You can't start saying, well, this is the sort of, it's kind of like we can't decide a minimal way to evolve if we don't really know what band's going with which and how they're related. So I think like charge-ordered systems might be an issue where the overlap between up and down look very different.
Any other questions? Yeah. And can the next speaker start setting up?
So in the kind of related to the previous question, in the cases you've tried, have you tried a case where the initial and final structure aren't related by just inversion or something like that?
I don't see why, well, at the moment for the current implementation, there are some restrictions as far as like if the lattice vectors are different between up and down, then you might have to do some additional things on the implementation side. Maybe it gets some Fourier interpolation to make sure you're matching up the right points. But so I haven't actually tried that, but in general, it should just be. I don't see why it wouldn't work. It's not restricted to that as long as you meet all the kind of requirements for the current implementation. Maybe even just a simple thing would go, instead of going directly between up and down, just as a test, go to some high symmetry structure.
All right, any further questions? All right, let's thank John again.